Here we go, Chapter 6, Confidence Intervals and the T-distribution. So we're going to just start right off with a video.
As students of statistics, we owe a great debt of gratitude to our friends at the Guinness Brewing Company. You see, there's a lot of science that goes into brewing beer, and in 1903, Guinness got all science-y in creating an experimental malt house at their brewery at St. James's Gate in Dublin, Ireland. At this experimental malt house, the brewers/scientists could grow all varieties of barley, from seed corn to harvest to malting to brewing to the final glorious product. In nature, barley has a lot of variability, and one of these scientists/brewers named William Seeley Gossett was very concerned about the variability of the barley plants, because you can't brew a consistent porter or stout if your barley is different from one season to the next. At the time, statisticians like Carl Pearson and Sir Francis Galton were using huge sample sizes, which meant that the parameters they were estimating approached a normal curve. But for a young brewer estimating barley yields, the sample sizes were small, maybe 3 or 4. And that is a problem, because small sample sizes do not look like a normal distribution. But fortunately, William Seeley Gossett solved this problem for us. He created tables, now called T-tables, that account for the variability of small sample sizes. Of course, he wanted to publish his tables, but then... So here's where the stories diverge. Some people will tell you that Guinness would not allow any of their employees to publish for fear of divulging trade secrets. Other people will tell you that Gossett published anonymously and that Guinness never found out until after his death. But according to the minutes of the Guinness board, Gossett was granted permission to publish with the stipulation that he use a pseudonym. And so in 1908, William Seeley Gossett published 2 articles in Carl Pearson's journal Biometrica under the pseudonym Student. And today, we still use Student's T-table whenever we do a T-test. So let us lift a glass to William Seeley Gossett, who proved that a small sample size is nothing to be ashamed of, and that some great things can come from statistics.
Okay, so as Gossett found when he was doing his barley tests, that there are some problems with the one sample z-test that we looked at last lecture. And the problem is that we usually don't know the population spread, the population standard deviation. And we need that standard deviation sigma in order to calculate the standard error for the mean. That's the sigma with the x bar on it. So we learned this formula very well yesterday, or last lecture. But sigma, that's the thing that sometimes we don't know. In fact, in real research, we almost never know. And so what we can do is we can use the sample standard deviation S in place of the population standard deviation sigma when we calculate the standard error for the z-test. But when we do this, there is a little bit of a nuance that is not trivial. And Gossett found that when he was trying to do this, use smaller samples and use the sample standard deviation to make a z-score, it wasn't that accurate. And it comes down to that smaller samples have more variability between sample to sample. So if you have a large sample like 300, it's not a hard and fast rule, but 300-ish in that range, the z-score with using sample standard deviation is okay. But when you have smaller samples, that z-score test that we learned in Chapter 5 is inaccurate. And so we only can use the z-test that we learned with the sample standard deviation if we have a large sample. That doesn't happen a lot. So when we have a smaller sample, the smaller that the sample is, the more skewness the sampling distribution. Because remember the central limit theorem that said the sample averages become normally distributed? That's as the sample size is large. I think the central limit theorem says large enough. And so if we have a smaller sample, that sample standard deviation underestimates the population standard deviation, and so it will overestimate our type 1 error. If we have a large sample standard deviation, population standard deviation, they're basically the same thing. But still, there is kind of a theoretical issue in that sample standard deviation depends on the sample. It's variable. It's different for each sample, where the population standard deviation, although we might not know it, is a constant. There is one number for the population standard deviation, sigma. But we can usually get away with using the sample standard deviation provided we have a large sample. So that sample size matters. So this was back in the early 1900s that Gossett, like the video said, figured out how to adjust the z-score with a different table, and he named it students t distribution, or it was named students t distribution, because when Gossett published his paper with those tables, the t tables, he didn't sign his real name because the brewing company didn't want their competitors knowing that they could use this information for brewing. He published this in biometrica and statistical journals, nothing to do with brewing. So on this slide, if you are interested, there's this link that has more information on the revolution that this led to in experimental statistics. So here is a picture that shows the normal distribution in the dark green. It's the highest peak. And then it has two other distributions drawn on that are also bell-shaped, but you'll notice that they are squished. They are flatter. The peak is less high and the tails are more high. This flattening is the effect of having a small sample. So if you have a large sample, like infinity, your t distribution and your z distribution, students t and the standard normal, are identical. But the smaller the sample, the more you have to flatten or adjust the distribution for students t. So we have a t with 13 degrees of freedom shown, and that's the middle one, and then the degrees of freedom 5, that's the flattest one. So I want you to see that the shape of students t distribution is still bell-shaped, it's still symmetrical, it's still smooth, it's just not as peaked, it's more flattened out. And the degree of flattening depends on the sample size. So similarities, both of these, standard normal curve Z, students T distribution, both of them have really, you would probably call them nasty formulas, but they do have mathematical formulas. They're symmetrical, continuous, bell-shaped, continue on to infinity, both have centers at 0. So there's a lot of things that are similar, and we can use both of them where area under the curve tells us probability. So we can use the t distribution the same way we use the z distribution. In fact, if you have a very large sample, they're nearly identical. The differences are there is only one standard normal curve z. Center 1, standard deviation, or center 0, standard deviation 1. However, there is a whole family of t distributions, and they are denoted with different degrees of freedom based on the sample size. So instead of just having one, we have many. Now I want you to think about our Z table in our book that we've been using. It has 3 pages to display it, and it doesn't go on forever. It only goes up to a Z-score of 3 or 4-ish, and then it kind of cops out. Because those tails keep going forever, but usually when you get back past 3 or so standard deviations away from the center, you've got very little area under the tails at that point. Well, that's 3 pages for one Z table. If we've got a family of t-tables. Do we want 3 pages for each one? Not really. So the table is actually set up differently than the z-table. It's more brief, so we can fit all of them on the same page for all degrees of freedom, which brings up degrees of freedom for the t-distribution. How do you figure out the degrees of freedom? Degrees of freedom is just one less than the sample size if you're doing a one sample t-test. Now, the book tries to go into more about degrees of freedom. I'm not going to talk a lot about them in this lecture recording, but I'd be happy to have a more deep conversation with you. It has to do, like when we did the unbiased standard deviation, that you have one less than the sample size pieces of information if you already know the mean. It also comes out of some calculus formulas. It wasn't just like someone thought, oh, one less sounds good. It has to do with derivatives and integrals and things like that. But for one sample test, the degrees of freedom are sample size minus 1. We'll see that the degrees of freedom are different when we have a 2 sample test as we move forward in the future units and chapters in the class. So this is what the table looks like for the t distributions, plural. There's lots of them. It's a whole family of distributions. So the picture at the top should look kind of familiar. We've got a one-tail test where all of alpha is in one tail, and a two-tail test where alpha is divided in half into the 2 tails. But it is still symmetric, and it's still centered at 0, still bell-shaped, still continuous. Now, in our book, the z-table was called table A1 because it's the first table in Appendix A. The t-table is table A2 because it's the second table in the Appendix A. So we're going to learn how to use this. I just want to point out the basics, that at the top it has this kind of sketch for us to follow. Then it has the top part of the table where you decide if you want one tail or two tail and what your level of significance. Remember, a level of significance is alpha. And then down the side, we have degrees of freedom. So each line on this table is for an individual set number of degrees of freedom. Instead of having 3 pages for each number of degrees of freedom, we have 1 line for each degree of freedom possible. It does not go on to infinity. This is just the first few lines, though. So we can calculate t-scores and use them in almost exactly the same way we did z-scores and z-tests. We are assuming that our scores, or our measurements, are still interval ratio. If you have Likert scales or ordinal scales, usually if they have 6, 10, 16 people, there's different cutoffs, a lot of levels, we can usually treat it as its interval ratio continuous score. But the formula for the t score is almost the same as z-score. Again, we're going to take our samples average minus our hypothesized mu population average. And when we divide, we need to divide by the standard error. But instead of using sigma, the population's known standard deviation, which we never know, we're going to use the sample standard deviation and divide by square root of n. So swapping out the sample standard deviation in place of the population standard deviation is the only difference in this formula. But we're going to call it t instead of z because we need to use the adjusted tables. And to do that, we need to also find the degrees of freedom, which is 1 less than the sample size. So, assumptions. There are assumptions that go with every test, every statistical model, because all models are wrong, but some models are useful. And the usefulness of any statistical test or model depends on how well the assumptions are met. And these assumptions should look fairly familiar. They're almost identical to the one sample z-test, one sample t-test. Both of them, number 1, require that we have a random sample, or at least is as representative as possible. Again, there's nothing we can do to statistically test if that's true, and there's nothing we can do to fix it. So this has everything to do with how you enroll participants in your study. The second assumption is that the standard deviation of the sampled population is the same as the comparison population. Again, this has to be something that is reasonable, but you cannot test and you cannot fix. The last of the 3 assumptions is that we have normality of the score that we're looking at. Now, with a z-score, we usually had a large sample, or should, and so the central limit takes over, the central limit theorem. If we have a smaller sample, the central limit theorem is less likely to take over, But it's also, on the flip side, also harder to determine normality if you only have a small sample. But we still have at least 3 ways to go about kind of judging if our sample looks normal or looks non-normal. And these are the same as we used before. We can plot with histograms, QQ plots, box plots. We can calculate or have the computer calculate skewness and kurtosis numbers. But again, there's not very good guidelines on what's too much or too little on skewness and kurtosis. But if we really need to or want to or are hard-pressed, we can run the Shapiro-Wilks test to judge normality of a population based on a sample. That's all the same stuff we did last chapter. Now, at this point, we're starting to have a lot of formulas running around and a lot of formulas that look similar to each other. And so I've put together our formula sheet. And I've just taken a snippet on this slide of the first part of that formula sheet. So if I go to our homepage in Canvas, I have the link to our class, which is also can be found on my personal website, sarahschwartzstats.com. So if you scroll down, remember down at the bottom are the table where you can get the links to the slides. But again, above that table of the chapter slides, for download, I have the lookup tables that are Appendix A in your textbook, as well as this formula sheet. So you can get the formula sheet there. It's several pages long because it's going to last us the whole semester. But the very top part of the very first page has the one sample tests. And these one sample tests are for the using the sample mean. Now we're going to hold off on the confidence interval side. I just want to look at the hypothesis test portion. So for a hypothesis test, our null hypothesis H0 is always that mu, population parameter, is equal to some value, which we often write as mu with a little 0 to denote that that's the number for the mean prediction or mean hypothesis or the null hypothesis. The alternative hypothesis, instead of an equal sign, is going to either have the not equal for a two-tailed test or a less than or greater than symbol if it's a one-tailed test. Again, we're going to go with two-tailed unless there's a good reason why we shouldn't. So I have our Z formula and our T formula. Now you'll notice they look very similar. The only difference is with Z, we should know the population standard deviation. For a t-test, we can use the sample standard deviation, but then we need degrees of freedom, which is 1 less than the sample size. And there's some notes off to the very end. So it says on the top line for Z, it says use if you know the population standard deviation, that's sigma, or when your sample is very large, like in the hundreds. The second line for the t-test says you should use that when you have a small sample, or are using the sample standard deviation instead of the population standard deviation. There's a little bit about Cohen's d. Let's just ignore that for the time being. So examples always help solidify. So here's a scenario. A physician states that in the past, the average number of times he saw each of his patients during a year was 5. So on average, patients came to see him 5 times a year. Probably not my general practitioner. Maybe this is a specialist. However, he believes his patients have visited him more frequently this year. So in order to validate or find evidence for his claim or statement, he's going to randomly collect some data. Now, we are just going to take this on face value that this is a random sample. I don't know how he would do this, if he had a database, if he could randomly pull them, but say this is true. So we have a random sample of 10 of his patients, and he looks in their charts or has his assistant look in their charts to find out how many times each patient came in. And these are listed in green on the screen. So they're 9, 10, 8. Someone was 0 and the highest was 15. So the question becomes, the research question is, do these data, the sample of 10, support his contention or claim that the average number of times he sees patients in the last year is different than 5? Now I want to talk about directionality here for a second. He thinks that they're coming more often. However, we're going to state the hypothesis that it's not 5 because that's the two-tail alternative. Being different than 5 allows for the opportunity that it could be more or it could be less, even though he has reason to believe he thinks it might be more. We're going to be conservative and go with the two-tail test. So we're going to use those same 6 steps of a hypothesis test we learned with our z-sample test. So the first is to write our hypotheses. Null hypothesis is always about the population parameters being equal to something. So here, our null hypothesis is that mu, the whole average this year of all people's visits, would be equal to 5. The alternative, again, we're going with the two-tail alternative, we're letting it be not equal to 5, even though he really thinks it's probably going to be more than 5. Now, these hypotheses should be written before we see the data. Now, looking at the data, you might go, it doesn't look less, but that's peaky. The second step is also after we've written those hypotheses to decide on our test and significance level. So now we're going to do a one-sample t-test for the mean. That's the whole point of this chapter. Last chapter, we did a one-sample z-test for the mean. Now, these kinds of tests, these one-sample tests, are very rarely used in real-world, actual live data analysis. And the reason is it's really not a great idea to use a hypothesis that is banking on a historic control. It's much better to have a control or placebo group. And we'll talk about that more in an upcoming chapter. But we're starting super simple with training wheels. So we're just going to compare our sample to a number, which the number here is 5, which we're setting as the historic control. So we're going to do, by default, we're always going to go with two-tail test, even in the present of some evidence that it should be one direction, and we're going to go with the default alpha 0.05, even though there's debate whether that should be the true cutoff we always use. So remember, when we run a hypothesis test, sketching a curve is great, and that curve and all of our math, everything is based on the null hypothesis being true. We always set that null hypothesis that nothing's going on, it's the same as it's been in the past, nothing to see. We always use that as our goalpost to look at our data. So the center of our normal curve is that null hypothesized value of 5. So state your hypotheses, specify your test, what type of test. Now again, we're going with a z-test because our sample is small, it's only 10, and we don't know the population standard deviation. We're using the sample standard deviation. And we can calculate that from the number. I don't want to do it by hand, so I'm going to show you how to use R to do it. So this is how you can use the power of R in a very small way to avoid having to do lots of button pushing on your calculator. So step 3 is to gather your data, to take a sample, gather your data. Now this was already presented to us on the previous page. So I've just taken all those numbers, those 10 values that we were told was our sample, and I'm concatenating it or using the letter C to combine those together and save them, that assignment arrow, as the letter X. So X is going to be stored in R in our global environment as the listing of these 10 values. And we want to compare them to see if this provides evidence that this sample's average can show us that the population is greater than or less than 5. So we need to know what our sample size is, what our sample average is, and our sample standard deviation. And we can use R to do this without having to type a bunch of buttons. So to get the sample size, that's the length of this vector or this concatenation combination of all these numbers. So the length command, the length function in R, if you just say length of X, it will count how many numbers are in that X concatenation. So this is our sample size N, and it's 10. Sample mean, we could do this by hand. We could use, our brain power and mental math or our calculator and add 9 plus 10 plus 8 plus 4, add up all these numbers in this concatenation, and then divide by 10, or I can actually just ask R, what is the mean of the X concatenation, the X vector, and it's going to add them up and divide by 10 all by itself and spit out 7.6 exactly. So I have a sample size 10 whose average is 7.6. Now our null hypothesis was that the average in the population is 5. Our sample happens to have a bigger average. Our sample is definitely having an average bigger than 5. But is that evidence that the whole population would have a sample bigger than 5? Maybe if I took another sample, maybe its average would be 2.1. I don't know without taking lots of samples, but we can get an idea based on the standard error for the mean, the spread within the sample combined with its sample size. So I can calculate that standard error, but using the sample standard deviation instead of the population standard deviation. So here's where R is really, really handy. I can ask for the SD, lowercase s and lowercase d is standard deviation function in R. So I can say, what's the standard deviation of X? And it will take all of these numbers and do the formula, take all the numbers, subtract the average, square them, add them up, divide by 9, and it will give us the unbiased standard deviation, just with 2 letters, SD, and then tell it what we want the standard deviation of. If nothing else, this is a big shortcut. So here I have my 10 numbers. Their standard deviation is 4.25-ish. Again, when we're working by hand, we have to really worry about using enough decimal places, because if we don't, we have round off error, and each step would give us a little more round off error. In the computer, it's really got this number 4.247875 to many, many decimal places, more than it's even showing us. So we don't have to worry so much about round off error. So again, standard error for the mean. We don't have sigma, but we can use S as our best guess, as long as we then call it a t-score instead of a z-score. So we're going to take that standard deviation and divide by the square root of n. So even though our standard deviation in our sample is 4 1/4, our standard error for the mean is 1.34-ish. So now we can find our t-score. Our t-score is our observed mean, that would be 76, minus our hypothesized nothing going on mean mu of 5 divided by our standard error. So before we go about calculating that t-score, that's really step 5. We should do step 4 first, which is to find the rejection region. And this is one we usually only do if we're working by hand, to find the rejection region. So this is where we need to figure out how we can use this t-table in a different way than the z-table. So here I brought it up. So the first thing you want to do with this t-table is you've got to find which row we're going to pay attention to. And the rows are based on the degrees of freedom. So degrees of freedom for a one sample test is always 1 less than the sample size. So if our sample size in this case was 10 people in our sample, then our degrees of freedom are 9. So we're going to go down to the row that has degrees of freedom listed as 9, and I've highlighted that whole row across. So that's the only row we're going to pay attention to for this sample. Now, usually in a z-table, there's pages and pages. We only get one line that only has 6 numbers across it. So this is a lot more brief. It only gives us a few of the values. Now, we have to look at the top part of the table to decide which column we're going to look at. So this is 2 questions. First, you have to decide, do you want 1 or 2 tails, and what do you want your alpha level to be? Now, always without any more information, we're always going to default to 2 tails, alpha 0.05. So I've circled those. That puts 95% of the area in the middle and splits the remaining 5% equally between the 2 tails. Now, the way this table is set up, you just look at the right column, look at the right row, and where they cross, that tells you your critical value. So now we know that if our t-score of our sample is observed to be bigger than or more extreme than this number 2.262, we will have a statistically significant result. So I'm going to go ahead and label this on a new normal curve. So our normal curve, again, is always centered at the mu of the null hypothesis. We're always assuming the null hypothesis is true. So it's centered at our null hypothesis, mu equals 5. And we just looked up in the table and we found that our critical value is 2.262 based on having 9 degrees of freedom, 2 tails, and an alpha of 0.05. So I'm marking the critical value. That is alpha 0.05 divided equally in the 2 tails, leaving 95% in the center. So I've marked that, 2 equal tails. from this, we see if our t-score of our sample is observed to be bigger than positive 2.262 or littler than negative 2.262, that would be a reject the null hypothesis. That's our rejection region. If our t-score falls in the center, closer to the center, then we would not have evidence against the null. So again, in the center is the rejection, is the fail to reject, and the tails is the rejection region. So I've gone ahead and I've used R to do my number crunching for me. So the t-score, again, we take the mean of our data minus our hypothesized value. Our null hypothesis was mu is 5, divide by our standard error that we found on the previous page, and it is saved, standard error, I saved it as SE so I could use it later. So now we get a t-score of 1.94. If I draw that on my normal curve, I see that it's not as extreme as our critical value. Our rejection region to reject the null requires that our t-score was bigger than 2.262. In this case, our data is not that absurd. It's not that extreme. Because our observed test statistic from our data is in the middle, we fail to reject the null. We have no evidence that the whole population has more than 5 visits per year. Now, to find the exact p-value, we have to go back to our table. Now, if you're doing a test on a computer, which we're going to learn to do today, it will give you the exact p-value to many decimal places. But if we're using this table, because degrees of freedom 9 only has 6 numbers there, we cannot get the exact p-value. We can just get an idea of what the p-value is, not the exact value. So again, we have a sample size 10, so we have 9 degrees of freedom. So we're going to look at that row for 9 degrees of freedom. Always, we're going to default to 2 tails. So I've circled the line with 2 tails and I've crossed out the headings for 1 tail. I'm going to totally ignore them. Now I'm going to look across that line, that row, across it for 9 degrees of freedom, and I'm going to look for my t-value. The critical value was the one under 0.05, the 2.262. My observed sample t statistic was 1.94. Where would 1.94 fall on that row? It would fall in the between 2 of the listed values. It's going to fall in between 1.833 and 2.262. So we not go to 9 degrees of freedom, look for where our observed t-score is, and go straight up. And then the heading, again, we're doing 2-tailed, will tell us what our p-value is in between. So if we look up at the top, we got 0.10 on one side and 0.05 on the other. This tells us our p-value is going to be a number between 0.05 and 0.10. It might be 0.07, it might be 0.083, it might be 0.061. This table cannot narrow it down any tighter than that. We know it's bigger than 0.05, but it's smaller than 0.10. So going back to our scenario, the final thing we need to do is write our conclusion, and we're going to practice in APA context, APA format, and in context. So we saw that we fail to reject the null. That is kind of a conclusion, but that doesn't count as your conclusion in real research. Your conclusion must be in context. Our conclusion should talk about visiting the doctor, these patients visiting the doctor. How many times a year, annual visits to the doctor? So we fail to reject the null of 5. So that means 5 is still on the table. It could be 5. We don't have any evidence that it's different. So our conclusion, this is one way we could write it. Again, there are multiple ways. Here's one wording. We could say, even though our sample of 10 patients had a mean of 7.6 visits per year, this could be due to sampling variation and does not provide evidence that patients have changed the mean number of visits per year. And then at the end, we put our t statistic and our p-value. Now, a t statistics, after the t, which is italicized in parentheses, we put the degrees of freedom. So it's always t and then parentheses degrees of freedom, z-scores didn't have that. And then equals our t observed score, which should be to 2 decimal places usually. And then after that, we'd usually say p is equal to a decimal number with 3 numbers. But since we're using the table, we can't get that fine-grained p-value. We can just say that the p-value is between 0.05 and 0.10. And I would appreciate if you write the smaller number and then the bigger number, even though it's the reverse order at the top of the table. And that's how you can do a one-sample t-test by hand. I'm going to stop this recording now, and I'm going to come back and make another recording about confidence intervals, and I probably will split up a third video that uses R on how to do these one-sample t-tests with R completely.